You denied the flashlight app access to your contacts. You felt good about that. It was a small victory over the surveillance economy, a moment where you looked at the permission prompt, thought about what a flashlight should actually need, and tapped deny. The app opened. It worked. You moved on. The implicit model in your head was that you had just prevented the app from accessing your contacts, and that permission denial was the end of the story. That model is wrong in ways that the mobile operating system vendors have made almost invisible. The permission you denied was one of several dozen ways that AP could learn things about you, about your phone, about the other apps on it, and about patterns of behavior that are functionally equivalent to the data you thought you had protected. The permission prompt is not a fence. It is a single locked door in a building with many windows, side entrances, and skylights. This is the reality of modern mobile application sandboxing, which is still a substantial improvement over the free-for-all of early mobile operating systems, but which has structural holes that the average user has no way to see. Let me catalog them, because understanding the actual attack surface is what separates meaningful privacy decisions from performance art. Start with the categories of data an app can access without prompting for any permission at all. These are what Android and iOS classify as normal or silent information, the kind of thing any app can read as part of normal operation. Your device model, your operating system version, your screen dimensions, your current locale and language, your time zone, your default keyboard layout in many cases, the list of installed apps depending on platform and version and target API level, your battery level, whether you are connected to Wi-Fi or cellular, the approximate performance characteristics of your device, your accessibility settings, your display scaling, whether your device is rooted or jailbroken via common detection patterns, uptime since boot, hardware sensor availability. Any one of these is innocuous. Taken together, they form what researchers call a device fingerprint. Studies from academic groups, including the Electronic Frontier Foundation's Panopticlick project, and subsequent mobile-focused research have demonstrated that the combination of this silent metadata is often sufficient to uniquely identify a device across app launches, across reinstalls, in some cases, and across different apps on the same device if those apps include any of the common analytics or advertising SDKs that hash this data into a stable identifier. Which brings us to SDKs. This is where the real story of mobile data access lives, and it is the single most underappreciated aspect of the permission model. When you install an app, you are not just installing the app's own code. You are installing every third-party software development kit the developer chose to include. Analytics SDKs, advertising SDKs, crash reporting SDKs, user engagement SDKs, push notification SDKs, fraud detection SDKs, in-app purchase SDKs, authentication SDKs. A typical consumer mobile app includes between 5 and 20 third-party SDKs. Each SDK runs inside the app's sandbox with all the permissions the app has been granted. Each SDK typically communicates with its own backend servers. Each SDK has its own data practices that the app developer may or may not fully understand. When you grant an app access to your location, you are granting that permission to every SDK inside that app. When you grant access to contacts, the same. The permission system does not distinguish between code written by the app developer and code written by a third party that happens to be linked into the same binary. An advertising SDK that collects location is, from the operating system's perspective, the same as the app itself collecting location. Research by Jonathan Mayer, by Serge Egelman's team at ICSI, and by numerous independent researchers has documented the flow of data from mobile apps to third parties. The 2019 ICSI study of the Android ecosystem found that thousands of apps collected and transmitted data in ways that, at the time, circumvented the then-current permission model through side-channel and covert channel techniques. Some used fingerprinting. Some read data from SD card locations written by other apps. Some extracted persistent identifiers from system properties in ways Google had not specifically blocked. Google has since closed many of the specific techniques that study exposed. New techniques have emerged. The Exodus Privacy Project maintains an ongoing catalog of tracker SDKs found in Android apps. You can look up any app on their service and see the list of embedded trackers. The numbers are often startling, even for apps from companies with strong privacy brands. Banking apps include analytics SDKs. Meditation apps include advertising SDKs. Weather apps often include as many as 6 or 7 trackers. The presence of a tracker does not automatically mean misuse, but it does mean that data flows from your device to multiple companies whose names do not appear on the app's install screen. Now layer in inter-app communication on Android specifically, which exposes another channel. On Android, apps can expose content providers, broadcast receivers, and services that other apps can query, with permissions managed through Android's intent system. This is the mechanism that allows, say, a share sheet to work, or an email app to be launched from a web link. It also allows one app to probe others in ways that reveal information about what is installed, and, in some edge cases, what those apps contain. Android has progressively locked down these mechanisms. The queries element, in manifest files, introduced in API level 30, requires apps to declare which other apps they want to interact with, and the system filters visibility accordingly. But the restrictions have loopholes, and they apply unevenly across device manufacturers, Android versions, and target SDK levels. The package visibility problem, specifically, has been documented repeatedly. Before recent Android versions, any app could enumerate all installed apps on the device without any permission. This was a reliable fingerprinting signal. An app that sees you have certain specific apps installed, dating apps, mental health apps, political apps, religious apps, medical apps, knows a great deal about you, even without reading any of their contents. Android now limits this enumeration, but has exempted certain categories of apps, like browsers, and provides the Query All Packages permission for apps that claim a legitimate need. That permission is granted generously. Search for apps that request Query All Packages on the Play Store, and you find many that do not obviously need it. iOS has a narrower version of this problem, but is not immune. The CanOpenURL API, which lets apps check whether a particular URL scheme is registered on the device, has been used to detect specific apps by probing for their URL schemes. Apple has limited the number of schemes an app can check without declaring them, but within those limits, fingerprinting through installed app detection still functions. Then there is the category of platform-level tracking identifiers. The identifier for advertisers on iOS, the IDFA, was for years a persistent per-device identifier that advertisers used to correlate activity across apps. Apple's App Tracking Transparency Framework, introduced in iOS 14.5, requires apps to request permission before accessing IDFA, and the majority of users deny it, which has materially disrupted the mobile advertising ecosystem. This was a real privacy improvement. It is also not the whole story, because in the wake of IDFA's restriction, the industry moved to fingerprinting-based identifiers that do not rely on the official API at all. These operate by combining the silent device metadata I listed earlier into a probabilistic match. Some data brokers have been open about this. Others do it quietly. The technique is imperfect at the scale of individual users, but accurate enough for advertising attribution at the aggregate level. Apple has issued policy guidance that forbids fingerprinting under their App Store rules, but enforcement is opaque and ongoing. Android's advertising ID has a similar history. Users can reset or disable it, but the same fingerprinting pressures exist. Let's talk about sensor-based side channels, because this is where the research gets genuinely surprising. Apps with access to motion sensors, the accelerometer and gyroscope, which on most platforms do not require permission, have been shown in academic research to infer keystrokes on the on-screen keyboard. The pattern of micro-movements as a user types produces signals that machine learning models can decode with non-trivial accuracy. Research from Newcastle University and others demonstrated this years ago. The attack has not been deployed at scale in known malware, but the capability exists, and motion sensor access remains largely unrestricted on both platforms. Ambient light sensors, barometer readings, magnetometer readings, all of these are accessible without permission. Each has been shown, in various research contexts, to leak information. Barometric pressure combined with magnetometer data can reveal floor-level movement in a building. Ambient light can reveal screen content in certain narrow attack scenarios. These are edge cases for most threat models, but they exist. Microphone access, which does require permission on both platforms, is the common fear. The empirical evidence is that consumer apps largely do not secretly record audio without permission, partly because detection would be catastrophic for the app's business. But microphone access, once granted, is often broader than users expect. On some versions of Android, an app with microphone permission could record even when not in the foreground until more recent restrictions. iOS now shows a persistent indicator when the microphone is active, which is a meaningful deterrent. Clipboard access is another surprise. For years, apps could read the clipboard at will. In 2020, iOS 14 added a notification when apps accessed the clipboard, and the result was a wave of disclosures. News apps, social apps, shopping apps, and countless utilities were reading the clipboard every time they came to the foreground. Many did this for legitimate reasons, pasting a copied URL, for example. Many did not. Android added similar notifications later. The Iowa lesson was not that apps were doing anything technically unsupported. It was that a capability users assumed was rare had been nearly universal, invisibly. Network-level behavior is another dimension. Apps make network requests. Those requests reveal which servers the app contacts. Passive observation of app traffic, even when encrypted with TLS, reveals the destination server and the pattern of communication. Researchers, and occasionally the apps themselves, have documented requests to servers that do not match the app's stated function. DNS queries, in particular, leak destinations even when the underlying traffic is encrypted. Encrypted DNS, DOH, and DOT mitigates this somewhat at the network level, but does not change what the app itself sends. So what do you actually do with this? First, reduce surface area. Fewer apps means fewer SDKs, fewer network connections, fewer permissions to manage. If you do not use an app regularly, uninstall it. The fastest privacy improvement on most phones is a purge. Second, prefer apps with strong privacy track records and transparent development. Open source apps, while not automatically safe, at least expose their code to scrutiny. Apps from developers with a single focused product tend to include fewer SDKs than apps from companies monetizing through advertising. Look at Exodus Privacy or similar tools to see what's inside. Third, on Android, consider a de-Googled distribution like Graphene OS or Calyx OS if your threat model and technical comfort allow. These systems provide finer-grained permission controls, including network permissions for apps, which no mainstream Android distribution offers by default. You can, on Graphene OS, deny network access to specific apps entirely, which cuts off SDK telemetry at the firewall level. Fourth, on both platforms, audit your permissions regularly. Settings reveal which apps have which permissions. Revoke anything that does not match your use of the app. Fifth, understand that permissions are a floor, not a ceiling. A denied permission blocks one specific data path. An app with no permissions can still fingerprint your device, read clipboard content under some conditions, query sensor data, and report it all to whatever backend it pleases. The permission system is worth using, but do not mistake it for privacy. The deeper truth is that the mobile app model was built for convenience and retrofitted for privacy. The sandbox is strong relative to the desktop era. The permission prompts are better than nothing. The transparency features in iOS and Android have materially improved in the last several years. But the economic incentive for apps to extract data has grown at least as fast as the protections, and the gap between what users think their permission choices mean and what apps actually do inside the sandbox has not meaningfully closed. The app permissions on your phone mean something, but they do not mean what the interface suggests. They mean that a specific labeled door is locked. They do not mean the house is secure. Treat the permission prompt as one small signal in a much larger landscape of data flows, and make decisions about which apps you install with the understanding that every app is a door you open yourself every time.